Okay, so we are trying to bound this quantity, and for us W again, remember, is a polynomial p x1 to xn, and we're trying to understand when is this quantity small, and we're trying to show this quantity is small as long as all the singular values associated with the tensor are small. So let's try to evaluate this quantity, and the things that will help us.
But before you start, is there any intuition?
Why?
So there'll be, I believe there'll be some algebra and it will be correct.
I do not know. I mean, unfortunately, I don't have any intuition. I mean, yes, I really don't have any intuition. I mean, being very honest here, the only part of the work which was our contribution was guessing the correct condition under which this thing should work. And once you know the right machinery, you just do the right algebra. I do not know why these things work out the way they work out.
So what you want to say is that, for this expression to be small, somehow the noise operator should not affect W very much. The derivative of W and the derivative of the noise operator applied to W should be about the same, right? Then this would be roughly 1, and the difference between.
Right. So then you are trying to compute basically the variance. Yes.
Yeah. So you're saying that W's which are not correlated with products, right?
So I'm thinking. Sorry. Is it true that derivative of the if I did not have L inverse here, then then this dw is always 1. Is that true? Because then it will be, I have to put p and q equal to 1, and oh God. So suppose I had just dw and dw. No, I don't see why that.
So why? Yeah. What is this, for example? What is dW? What's the norm of dW? If W is expectation 0, variance 1, what's the norm of dW?
What's the norm, like what's the 2 norm of dw?
Yeah, because that's
Uh,
what it will be if you didn't apply that.
Okay, we can evaluate it from here. I don't know what it is. We can evaluate it from here. So you put dw here, okay, and you're dealing with polynomials of, let's say, the same way polynomial. So you put p equal to q. So then it's p square summation r minus 1 factorial. You take this sum, and then you have this p plus q minus 2r. Okay, so the point is that if p and q are the same, if r equals at the last term I p plus q, r equals p comma q, this will be the constant term, which will be the variance really, which will be the constant term, the expectation of dw.
So it will be 1.
But other terms are going to exist, like this p plus q minus 2r for r smaller than the minimum value of p comma q. So I don't think L inverse is the issue. I don't think L inverse is the issue. It's not. I mean, dw d L inverse, the L inverse, the attenuation of the noise operator is required to even make make the constant term the correct number 1. Is the presence that if these polynomials for r smaller than minimum of p and q, these will be non-zero polynomials. These will be non-constant polynomials whose whose variance you are trying to bound.
That noise operator will attenuate them.
The noise operator will attenuate them. The noise operator will attenuate the higher degree polynomials more than the lower degree polynomials.
So what you're really trying to bound in 1 minus this difference is the contribution of all the non-constant terms.
1 minus the important thing is that if r equals p, or suppose p and q are the same, when you look at r equals p comma q, so this contraction product is then just taking the inner product, which is just the variance. When r is smaller, you are taking the matrix, you are taking a matrix multiplication, you are taking a non-trivial matrix multiplication, and that kind of is obviously going to be small if all the eigen singular values are small. Then there is, like, you are trying to then A times B. If you take two matrices A and B, then the Frobenius norm of A times B is upper bounded by Frobenius norm of A times the maximum singular value of B. So if any of those singular values, this is pretty much the reason why this calculation works out. Why does that help? Why is the singular value being smaller, this non-trivial factorization, useful? I don't know. I don't have an intuition to give. I mean, I don't have one. Not that there's a complicated one which I can't give, I just don't have one to give. It's a great question, I just don't know why this calculation works out. I guess yes, but if you're actually trying to just do the calculation, it's dw dl inverse w. So you can first just use this quantity, this df dg, this calculation, to show that expectation of dw dl inverse w is 1. So the because all terms here, consider the summation, p and q are the same. So dl inverse p and q are the same for us. When you take the inner, when you put r equals p equals q, this term is just a constant, and it's just taking the inner product of the two vectors, which immediately implies, which immediately gives you the 2 norm of this, which immediately gives you the variance of w. And all other terms, or for r smaller than p comma q, you have I of p plus q minus 2r, and these are all Hermite polynomials at a higher level. Their expectations are 0. So you get that expectation of this quantity is 0. Sorry? What is the variance or something? What I'm trying to bound is the variance. Yes, I'm trying to bound the variance of the inner product. Exactly. I'm showing this expectation is 1. The expectation of this quantity is 1. So when I'm trying to upper bound, what I'm trying to upper bound is just the variance of this quantity. And just to see that expectation is 1, we just observe that if I take expectation here, the only term that survives in this entire thing is r equals p equals q. That is the only term which survives. Everything else, the expectation of that thing will vanish. And when you put r equals p equals q, all these terms, these terms will vanish. You will have a p minus 1 factorial. So you'll have a bunch of constant terms which are required for the normalization. And then you are taking I of 0. So that's just a constant. You're basically taking what is the constant inside. That's the inner product of f of the tensor corresponding to w with itself. But that's but the earlier relations there, which says that if you take the inner product of the two tensors, that's just the variance of the quantity. So you get 1 there. So that shows that the expectation of this quantity is 1. And now you want to upper bound the variance. So when you're trying to upper bound the variance, you again got to, so this formula is if p is greater than q, but this is the formula if p equals q. So for the moment, let's just consider we are dealing with a homogeneous polynomial. So we are just dealing with, there is just one level present. We don't have multiple levels. Otherwise, you use these formulas in tandem. Then you are trying to understand expectation of dw minus dl inverse w square. So g you can put as minus L inverse w here. This quantity will basically give you the inner product which will come out to 1 really. This is the quantity which will come out to 1. You can just do the algebra correctly. And plus now you have r equals 1 to p minus 1, this entire quantity. These are all constants, right? Because we are dealing with constant degree polynomial. This quantity is a constant, this quantity is a constant, this quantity is a constant, this is also a constant. And what you will be dealing, the important thing is that you're dealing with contraction product of the two tensors, where there is a non-trivial contraction happening, r equals 1 to p minus 1. And when you are dealing with this contraction, so this is the exact place where the small singular value comes in. You have we know the singular values of the corresponding tensors are small, meaning that if I take any matrix, if I consider any flattening, non-trivial flattening of the matrix, I'm taking non-trivial because R is non-trivial here, the singular values of the singular values are small. And that means if I consider, I'm basically taking matrix multiplication of two matrices, each of which has Frobenius norm at most 1, but both of them have a Frobenius norm at most a constant dependent on t, some scaling number is there, but each of them has singular value which is at most epsilon. And now we are just saying the Frobenius norm of A times B is at most the Frobenius norm of A times the maximum singular value of B, or vice versa. You can do it either way. And thus each of these terms inside is upper bounded by epsilon square or something. And the only constant number of terms you're adding up. So up to a factor like d factorial times epsilon square. So you get this entire quantity. When you evaluate all these quantities, you do the algebra, you will get epsilon square. Sorry? What do I know for f? So for us, f is w, g is L inverse w. So when what is L inverse of w? When you take a polynomial, L inverse of the given thing is f. So let's just consider that f is a Hermite polynomial. Let's just consider f is a homogeneous polynomial. What will be the the singular value of this is not going to change under the action of L, right? It's just attenuated by a factor of q. So why is it going to change? So you know the same thing about g as well. G is L inverse of w for us. This is pretty much the proof. Do you want me to go into more details about how this algebra is done?
Given this proof, you could come up with a condition.
Sorry?
So this condition that you came up with in your penalty, you could also extract it from this proof.
Yeah, yeah. If you actually just came to this point and then you said, okay, now what do I need to do to make this condition, to make the numbers go to 0? This is one of those conditions. Yeah, so if you have come to this point, then you can do it. Yeah. Unfortunately, I don't have any intuition to give us why this calculation works out. Expectation of w was 0 was used at several places. One is that when you look at proof of that, when you look at that, when you do that equality, that at some point uses that expectation of w is 0, like expectation of p has to be 0 for some integral to be bounded. And even before that, just the fact that you are using Stein's method, the way we use Stein's method, it used that expectation is 0. If expectation was mu, there would be another factor. So there are lots of places we use that.
Is expression like this, are there this kind of inner product in the case again the Boolean cube and where the noise operator is the Boolean noise operator, not the this one appears anywhere?
Not that I know.
The inner product of the gradient with the gradient of the noisy phi.
Not that I know of. Not that I know of. I don't know. The inner product of some of the I don't know. Some of the gradient only appears in algebraic complexity things, and noise appears in analysis of Boolean function. I don't know how it.
Well, you just take every value. So you average you have some function on the Boolean cube, and you average it over. So its value at the point x will be the average of the value of the function over all inputs, where you weight them according to the Hamming distance from x. So that's the standard noise operator.
That is just the Laplacian of the hypercube.
What?
Laplacian of the hypercube. What about it?
Yeah, sure. Anyway, yeah. So you can describe it in a way similar to the Uhlenbeck. Yeah. So I mean, since it seems to appear here completely naturally as capturing this maximal bound you get for any function. I mean, yeah. Just wondering if there are analogs.
Yeah, I do not know.
If you've ever seen this inner product appears in.
Yeah, this action of like first applying some noise and then taking a derivative. You're taking the discrete, yeah. For Boolean hypercube, you have to take the discrete derivative. For the continuous derivative, I think people do it, right? Because the noise and this derivative, I'm pretty sure that the continuous derivative and the noise appear together, but in some analysis of Boolean functions. But the discrete derivative, I can't think of. Okay, so when you apply noise, sorry, wait a minute. So when you apply noise, you take the function with a Boolean out. Suppose even if the function is Boolean, when you apply noise, the function doesn't remain Boolean anymore.
No.
Right. So now you have to take the discrete derivative, which still makes sense. So you're considering a function from gf2 to the n to r. makes sense then, not that there
Just
isn't.
to calculate it and to see if it matches one of the known quantities.
Probably. Yeah. Yeah, maybe maybe it's implicitly done. I don't know. I haven't seen this quantity.
But there you would not lose the property of the Hermitian polynomials, the Hermite polynomials. Derivatives there are not going to be ruled
No,
as
of course you use Fourier.
Yeah, Hermite polynomials make sense only with Gaussian
Hermite
base.
suits Gaussian space, and Fourier was transformed to suit the Polynomial.
Yeah. Well, again, if you're dealing with GF2, then Fourier polynomials of just the linear part. So, if you're dealing with GF2 polynomials, the Fourier thing is.
No, I mean, you write them as polynomials of degree n, right? The basis is all monomial.
Okay.
Yeah, it's the
Fair
same.
enough. Right.
And if your polynomial was of degree d, you don't need more than the d. Yeah, seems very similar. It's just, it begs for analogy. Maybe it's not. I don't know.
Yeah, I don't know.
Over counter it.
Yeah, maybe. Yeah, maybe.
Your
So.
original motivation was to deal with the Boulan cube.
Right.
So you moved to the Gaussian, which is easier, but it seems to suggest that maybe such inequalities or such bounds are present.
Yeah, maybe. Yeah. This is. Yeah, so there's applying noise operator and then trying to understand the elements. Yes. Yeah, I mean, at least the quantity. Yeah, I mean, I agree. Like the tensor rank as such, even if it's there, it's very hard to understand what's going on with it. But this quantity, well-defined quantity, I mean, it either has a meaning or doesn't, but it cannot be hard to see what's going on here. Like,
or just the expression with an arbitrary function g in the Boulan case, whether it's bounded by something that's not, well, g doesn't appear at all, and there's just some kind of product of similar.
yeah. This is okay. Good action.
So okay, I guess we are in the question period, right?
Well, there is.
You have what's your next?
Well, the more technical part of the paper remains now, like doing the combinatorial decomposition. Actually, this was just the central limit theorem. So we just So at this point we.
So you can continue to what you plan to say.
Yeah, I mean, I can stop here either as well. So okay, I'll just say whatever happens after this. So we have Okay, so at this point we understand when does a polynomial look like a Gaussian. Okay, this part was already known in some way or the other, in some other sense. So it was, for example, known by this famous paper of Nualat and Pecati, the fourth moment theorem, which says if you are dealing with a so whatever I've said doesn't need homogeneity, even though I assume for some part of calculation homogeneity. That if you are dealing with a homogeneous polynomial with a Gaussian space, mean 0, variance 1, then if the fourth moment is 3 plus minus epsilon, then the law of this polynomial or the random variable differs from the standard Gaussian by root epsilon. Doesn't matter what the degree is. This is a remarkable theorem because fourth moment is 3, so fourth moment gives a very nice characterization. That theorem requires, I think, really requires you to be a homogeneous polynomial. Even more than that, the reason why we couldn't just simply use that off the shelf and had to actually see if there's some other characterization is, we are still trying to understand, you are given a polynomial. Suppose it doesn't look like a Gaussian, what do you do then? You need to do something. If it looks like a Gaussian, wonderful, you know the answer. If it doesn't, you would like some sort of a decomposition. We are trying to do deterministic approximate counting. So we are given a polynomial and you asked what fraction of times is it non-negative on the Gaussian space. It looks like a Gaussian, you can just evaluate what fraction of times is it greater than or equal to theta. If it doesn't, what do you do? And the answer, well, so hopefully the answer is that if it doesn't, it permits some sort of decomposition, and then maybe we can. Okay, so if we just look at this theorem, it is already giving us some idea of decomposition, that you take the polynomial, if it's not looking close to a Gaussian, means its singular value of the polynomial must be large, meaning there must be some part from degree 2 to degree d which such that the corresponding tensor has a large singular value. Large singular value means, and as we have seen earlier, is that that part has a correlation with product of lower degree forms. So suppose I was just given a degree d polynomial and I was suppose its law doesn't look like a Gaussian, then I can say that f, the polynomial, looks like epsilon times p1 p2 plus r. R is a remainder term with smaller variance, say variance 1 minus epsilon, and p1 and p2 have strictly smaller degree. Okay. And the idea is, okay, then we can recursively do this thing, recursively we do this thing, and at the end, hopefully, if our decomposition works out correctly, we can just repeat this and we will end up writing a polynomial as a given polynomial as a combination of constantly many polynomials, let's say, as a sum. The combination is sum and products are also involved, right? I mean,
yeah, so the list will have, so basically sum of products.
Sum of products, yes, it's a sum of products, it's a combination.
The products will be a Gaussian.
Yeah, where each of the individual things behaves like, okay. So the question, okay, so it doesn't mean, again, I'm writing as a sum of products of individual terms, each of which looks like a Gaussian. Doesn't mean the sum of products looks like a Gaussian. But what will it look like? Okay, it doesn't look like a Gaussian, or it's not like these are all independent Gaussians or something. But then there is another hope that one can say that, okay, maybe, you know, it doesn't look like a Gaussian and it should not look like these variables, these individual leaves should not look like independent Gaussians, and for obvious reasons. Maybe there is a non-trivial correlation there. But is this the only thing that is there? Meaning, suppose I have expressed P as sum of products of individual polynomials, where each of these polynomials satisfies this small singular value condition. Does it mean that the joint distribution of these individual polynomials looks like a multivariate normal with the correct mean vector and covariance matrix? That can possibly be true. The earlier thing, they cannot behave like independent Gaussians because they have non-trivial correlation probably. But maybe the joint distribution does look like a Gaussian. Looks like a Gaussian with the correct mean and
all the things you are summing up.
all the things here. Okay, sorry. So since this is no longer required, suppose I have managed to express P. Let's say I have exactly managed to express P as pi1, pi2, pid, di equals 1 to k. Okay. So k is a constant. Let's say k is a million, and di's are all we want. Din is a number less than equal to 100, and let's say alpha some I. Okay. Alpha is a real number, and all these polynomials are so in all I have summation di polynomials. This is again a big constant. In all I have summation di polynomials, and each of these polynomials satisfies the maximum small eigenvalue condition, small singular value condition. I want to say the joint distribution of pi1, pidi, so p1, pi, and then I extend it from I equals 1 to I equals k. So there is a huge number of polynomials. The joint distribution of all these polynomials looks like a multivariate normal of summation di dimensions with the correct mean vector and the correct covariance matrix. That can possibly be true. Yes. If it is true, then I can say, well, if it does actually look like a huge multivariate polynomial, I can morally replace all these variables. See, once you have a multivariate polynomial with these many dimensions, which is again a constant, I can just say, well, now it's a constant dimensional problem, right? Because a multivariate now it's just a constant dimensional problem. So I can just replace all these variables by the corresponding variables from the multidimensional normal, and it again becomes a constant dimensional problem, which I'm trying to decide whether this number is greater than equal to 0 or less than equal to 0. What fraction of times is greater than equal to 0?
Yes, but it's a polynomial in constant dimension over the real number, so
You get
clear that it's solvable.
It's solvable because I mean up to arbitrarily small error. Suppose I tell you I have 5. Suppose I give you an explicit covariance matrix. Okay, so you have 5 cross 5 dimensions, and I give you a vector, and I say x1, x2, x3, x4, x5 comes from this multivariate normal. And now I say what fraction of times is twice x1, x2 plus 4 times x3, x4, x1 plus 7 times x5 greater than or equal to 11? I'm just asking you this question. Now, this is the kind of question we are really asking, and I'm saying, well, this can be solved because of, I mean, we prove it in some, but you can compute this probability up to arbitrarily good error and constant time. You can discretize the space. The space can be discretized because it's a Gaussian, it's continuous, it's a PDF is continuous, you can discretize the space and you can compute it to arbitrarily good errors.
So what condition do you have on these PIs? I mean, you have to say that they arose from this decomposition. I mean, if you just took many polynomials.
So I'm saying, suppose all these conditions, all these polynomials are maximum, have small maximum eigenvalue. All these polynomials have small maximum eigenvalue. Then I'm saying, can I that?
Oh, okay. That's the only condition.
That's the only condition. That's the only condition. Still, you're correct that you cannot simply just say that just because first of all, in what metric are they? Does it look like a Gaussian? All that is very necessary. So, in what metric does it look like? Here I'm saying I'll just plug in the same values. I mean, here I'm summing up these numbers, taking products. Will it remain in the correct metric? Will it work out? But the answer is yes, it all works out correctly. So, really it all works out. Kind of, there are multivariate versions of of this Stein's method, Malliavin calculus theorem I wrote, with not total variation distance as a metric, but as a weaker metric with test functions which have bounded second derivative. But all that works out. The moral of the, so I'm saying, okay, that's all technical part of like a few pages, but all that works out. The moral of the story of that part is that it is indeed true that if you can split the polynomial into and express it as a combination of polynomial combination of polynomials which all have small maximum singular value, it will all work out. The main issue is the following, that when you do that errors of when you do that theorem exactly, suppose the number of polynomials you have created is k, and the maximum singular value of each polynomial is epsilon. You must be paying something in terms of the error, right? The number of polynomials you have created and the maximum value. And the error term comes out to k square times epsilon, order of k square times epsilon. So, for this entire conceptual thing to make sense, k must be smaller than 1 over root epsilon to make any sense. So, now what we are really trying to do is that you are given a polynomial and you are trying to break it as a combination of polynomials, all of whose maximum singular values are epsilon, at most epsilon, for some epsilon, and the total number of polynomials you want to create in the process has to be strictly smaller than 1 over root epsilon. That's not such an easy thing to ensure, really. In fact, I don't, I mean, it might not be possible. I mean, how do you ensure that thing? Because say it's not in general, you cannot control these two parameters arbitrarily well. And this is pretty much the harder part of the paper. How do you actually do this kind of a thing? And because the number of parts and the quality of parts are competing parameters, right?
So it is true.
Sorry, you.
It is true.
It is. You can do it. You have to. But so there's a part you have to. It may not be. So even the statement of the decomposition is somewhat delicate to state. It may not be true that I give you an epsilon, and you can always decompose it. It is not, the following statement is not true, or not true that I know, not that I know of. It is not true that if I give you a polynomial and you give me a parameter epsilon, I can always express the polynomial as a combination of epsilon eigenregular polynomials. Let me call these polynomials with small singular values eigenregular, as epsilon eigenregular polynomials or with 1 over epsilon, 1 over square root epsilon such polynomials. That may not be true. What is, however, true is that we can. That there exists, suppose you give me any parameter eta, I can always find another epsilon prime dependent just on eta, such that I can decompose it into epsilon, each resulting polynomial will have maximum singular value at most epsilon prime. The number of parts I'll create will be some k prime, such that k prime square times epsilon prime is less than or equal to eta. So, it's really like you have to create a sequence of parameters, and all we can show is that one of those parameters is going to work out in your favor.
How small is that epsilon prime going to be?
The best, well, so in the paper we do not do anything. We just show there exists such a thing by, and I think the crudest bound you can get is some Ackermann type dependence. The best bound we can get is probably some Ackermann type dependence.
But you need some bound to have an algorithmic result?
Yeah, it's constructed. I mean, the bound you can, I mean, it's a constructible bound. It's not like, you know, it's we show that the bound exists and that it can be. We don't give an explicit formula for what the bound is, but it can be done. It can be constructed, and yeah, I mean, if you just do it crudely, you will see it's upper bounded by some Ackermann type function. Just for the moment, so I'll just like to, I mean, either we can stop here. I can try to give you some basic idea of how such a decomposition can go. Okay, I'll use my time. Okay, so let's do take one. So you're given a polynomial, and we are okay. You're given a polynomial. The singular value turns out to be small, smaller than epsilon. Excellent. You can stop right now. Everything is worked out. Else you take a polynomial and the singular value turns out to be larger than epsilon. So then maybe you can write down. Then it's easy to show that you can write it down as some epsilon, some eta p1 p2 plus r. And the condition is that and you will get that variance of r is strictly smaller than 1 minus epsilon, and roughly eta is going to be a number larger than greater than equal to epsilon. Okay, so you can break it off. Basically, I'm just stating nothing but if a matrix has a large singular value, that means you can take out a rank 1 component out, and whatever remains has to have Frobenius now smaller than 1. Now, I can recursively forget about, suppose even if p1 and p2 were perfectly eigenregular, maybe like, you know, they had their maximum singular value was 0, which is like only possible for linear form, but let's say it's 0. You will still have to work with r. Maybe r still has a large singular value, and you do it 1 over epsilon times, and there is nothing better you can really do. You probably have to do it 1 over epsilon times. And by the time you finish expressing this polynomial, you have some alpha I pi1, pi2, where all these things have really great eigen. So maybe, okay, so sorry, 0 is not good enough. Sorry, maybe these p1 and p2, they have all maximum singular value upper bounded not by 0, by let's say by epsilon, and you have 1 over epsilon such components, and now it's going to fail because k is like 1 over epsilon. So what do? I mean, this is a real problem. You cannot. There are competing parameters, and the first idea really is that. I mean, I think the main idea really is that. So you do this decomposition, okay? So you take this p eta p1 dot p2 plus r. Right now, don't worry about the p1 and p2. We have made some progress here. We have certainly lowered the degree of the two parts. P1 and p2 have strictly smaller degree. So let's say p is of degree 3. Let's say degree 3 itself has a problem. Now you work with r. So eta 1 p11 p12. Then you get eta 2 p21 p22. You keep going until you come to this remainder term r, which is one of the two things could have happened at this point. Either the variance of r has become really, really small. It is true, right? I'm removing eta variance at each step. So after 1 over eta square steps, certainly the variance has to become very small. Okay? If the variance has, suppose it goes on for 1 over eta square steps or something, the variance of r has become very small, and that's excellent. Then I can just say, you know, I can remove this r part. The polynomial will be changed from p to p prime, but because I'm removing such a tiny variance part, the law of p and the law of p prime are really the same. That can be shown by these anti-concentration type theorems and concentration anti-concentration theorems. And this is good. This kind of a thing, if it happens, is great for us, because now I have created 1 over eta square parts definitely, but I have come down 1 full degree. Now all the parts have strictly smaller degree. So if this continues for d steps, I will only be left with linear polynomials which have eigenregularity 0, which have maximum singular value 0. So this is a great step for us to happen. Another great step that could have happened for us is maybe, I do it for 2 steps, and the third time I find R has value, maximum singular value at most epsilon. Now I have just 3, and maybe now, now if P11 has maximum singular value, let's say epsilon, P12 has value epsilon, it need not be, but suppose in a good scenario these have maximum singular value at most epsilon, then I have 5 polynomials with maximum singular value again epsilon. So this is again good for us. K is 5, K square is 25 times epsilon, that's again good. What can really be bad is that we somewhere stop in the middle. We have created enough parts, so something like, maybe this goes on for like 1 over square root epsilon steps or something, or 1 over epsilon to the 2/3 steps or something. I have created too many parts, but by the time I stop here, I have created 1 over epsilon to the 2/3 many polynomials. So now K square times epsilon is really, really bad. And I haven't made progress in the sense I cannot drop the term for R. I cannot say, oh, R has small variance, let me drop it and I have moved a strictly smaller degree. I cannot. So this seems to be the really bad case. And the main idea to work around this is the following. You do this step for you continue doing this thing, and you look at the time when you reach R. If either of the first 2 steps happen, you are happy, something good has happened. Else what you do is you look at, if R doesn't have small variance, if R has small variance, you could have dropped it, you have made progress. If R doesn't have small variance, you look at the variance of this part, the variance of the part you have chopped off so far. If that variance is really, really tiny, let's say eta, then you can remove that part. Okay? If I remove this part, I remove variance eta, I'll be left with 1 polynomial. If I remove this part, I'm again removing only a very small part of the polynomial, but I'll be left with only 1 polynomial with eigenregularity epsilon. That's fantastic. Again I can, the number of polynomials I've created is 1, while the eigenregularity I've created is epsilon. So this is a good step. So the only way I can continue, the only way I cannot do either of these steps is that this polynomial, the part I have chopped off so far, so the first stage of the part until I have arrived at R, has reasonable variance, has variance eta. And now I have reached epsilon regularity. The number of parts I have created is probably 1 over epsilon to the 2/3, and the variance of this part is substantially large, it is at least eta. But now what I do is, now I will say that this part we have made progress, we have certainly lowered the degree. So why don't we do this? Now with this part, if we are in such a bad situation, we start with we start a decomposition with R with an even smaller regularity condition. Now we start, okay, so now we have reached here, we see it's epsilon regular, but maybe it's not epsilon 2 regular, but epsilon 2 is much smaller than epsilon 1. Okay. If it's epsilon 2 regular, again it's a great condition, because if this is epsilon 2 regular, this is really small. Oh sorry, I'm again using the word regular. If the maximum singular value is epsilon 2, this is really good, which is much smaller than epsilon, because then again the number of parts you have created can compare favorably with the maximum singular value. So if not, you start now decomposing with.
Which epsilon did you use for the pi1, pi2?
So I started with a singular value. I started with a target singular value epsilon. I kept doing the decomposition until the remainder part has either small.
Is eta smaller than epsilon or bigger than?
Which eta ones? Oh, these are at least larger than epsilon. I know that part. These are at least larger than epsilon. The point I'm trying to make is, this part we have made some progress, because we have gone down at least a degree smaller. This part is the tricky part, because I have reached epsilon regularity at the cost, epsilon maximum singular value, at the cost of introducing so many new polynomials. So if I apply a central limit theorem at this stage, I can never win. So now the idea is, why don't I now work on this part again with the even smaller singular value epsilon 2, and I continue doing this sequence. Now this inner decomposition we saw can proceed for at most 1 over epsilon squares steps, but since the only reason I proceeded to the next stage was because this part has variance at least, the part I chopped off has variance at least eta, the outer sequence of decomposition can proceed at most 1 over eta square stages. So what we have to do, okay, I'm really running out of time and it's probably not possible to explain this thing in detail. We create this whole sequence of parameters epsilon 1, epsilon 2, epsilon k, where it's a rapidly decreasing sequence. So whenever you stop, maybe you stop after 5 such outer loops, the number of parts you have created will always compare favorably with the part with the maximum singular value of the highest degree part, and in the other parts you have made progress because you have lowered down the degree. So you have to create this sequence of parameters, and then you have to deal with these things, which means you have to create another sequence of parameters, and this is the reason why this bound just becomes like insanely large. I mean the bound, well, small really, it doesn't become large, it becomes insanely. So yeah, I mean we are not setting the precedent going to with bad values, but I think this is worse than Zemerity's thing. Really, this is not even a tower. This is worse than that. Maybe there's a smart way around all this. Like, I'm sorry I couldn't explain the last part in detail, but really, at the end of the day, maybe the one line I would like to say about this decomposition is, you may not be able to choose favorable. Avi pointed out that this is already done in case of strong regularity lemmas and other things. But yeah, you may not be able to always decompose an object with favorable parameters, with quality parameter and the number of parts in arbitrarily good fashion. But you can always consider perturbing the object, and then possibly you can do it. You can perturb the object by a tiny bit, and then the number of parts and the quality parameter can be chosen competitively. And this is exactly what is done in this sense, that we are always removing tiny parts and doing this. Yeah, the decomposition lemma would have taken a long time to do, but thank you.